right, so we're talking about inverses of one-to-one functions, and I'll explain what I mean by that in a little bit. Okay, so finding inverses graphically. It says if AB, a point AB, is on the graph of f of x, of your function, then b comma a is on the graph of its inverse, f of -1 of x. Okay, so just notice what happened. My x and my y flipped places. That's what's happening here graphically. So, easy way to show you this is just give you a table of x, y values. And let's just do 1, 2, 3. All right, now what happens here? If I put in a 1 into this equation, 1 goes into 2x, and that becomes a 2. 2 times 2 is 4. 3 times 2 is 6. Okay? Now, the question is, are these inverses? Well, how do I know? They would be inverses if I can just flip the x's and the y, and it's still a true statement. So over here, my x's will be what were my y's over here. So if I put in a 2, a 4, and a 6, let's just see if my y values come out to be what my original x's were. If that's true, then these guys are inverses. So let's just see. 1/2 of 2 is 1. 4 times 1/2 is 2. 6 times 1/2 is 3. So you notice in our two tables, x and y's have flipped places. So yes, these are inverses. Now, what I want you to know that is this. On my graph, graphically what's happening here, if x is 2, let's just graph this really quick. This is going to be a steep little climb here, okay? This one, if I graph it, this is going to be a little bit flatter. Now, my drawings are not great, but what you should see is that this is a steep slope of 2, and this has a slope of 1/2. And really what's happening with inverses is they are basically folded along the y equals x line. Let me just show you what I mean. I'm going to show you. If the y equals x line does this, if I took this curve and I folded it across there, it would look like this. And if my y equals x line is here, and I took this curve and I folded it this way, it should look like my original equation. So graphically, they're folding along the y equals x line. That's what's happening visually. On a table, you're going to see the x and the y's flip places. So make sure you kind of get that, all right? So in your book, you're going to be looking at graphs, and could you fold them along this y equals x line, and would they be inverses? That's what you're looking at. And you're looking at table values as well. All right, one-to-one functions. A function is considered one-to-one if it has an inverse. So how do you know? Well, a function has an inverse function if and only if, this is not a typo, guys, if and only if no horizontal line intersects the graph more than once. So for instance, if I have a line like this, it's a function. If I put a horizontal line through it, it only hits in one place. This means it has an inverse function. It exists, okay? A parabola, however, that's a function as it is, but if I put a horizontal line, it's going to hit in two places. So an inverse function does not exist, okay? It does not exist. An inverse exists, but it is not a function, and that's a difference you don't need to worry about. Right now, I just want you to look at the horizontal line test. Does it pass or does it fail? If it passes, it's considered one-to-one. If it fails, it is not. So look at these. Do these functions have an inverse, or are they one-to-one? Those are interchangeable, okay? Horizontal line test, look, it's going to hit two places, so this one is not one-to-one. Look at this cubic guy. If I put a horizontal line through it, only hits in one place. So will it have an inverse function? Sure will. It sure will, okay? Okay, the last thing we need to talk about is verifying inverses, okay? One way you can show that two lines are inverses or two functions are inverses of each other is by doing compositions of one another. Okay, compositions. If you take a composition, we just did these the day before. If you take like you have two functions, f of x and g of x, you need to know, are they inverses? Well, if you take the f of g of x and you solve it down, and you take the g of f of x and you solve it down, those two should be equal if they are inverses. Okay, so let me just show you what I mean. So we're going to do f of g of x first. Okay, so here's f, here's g of x. So that means I put in g goes into f, right? So I'm going to replace this x with g. If I solve that down, I get x minus 3 plus 3, which is just x. Okay? Now we do the reverse, g of f of x. So I take the g function, instead of x, I replace it with f of x. So I put x plus 3 minus 3. Simplify it, and I get x. Since they both came out to be the same value of x, they're inverses, right? Let's try another one. Same idea. F of g of x first, taking g, putting it into f. So that would be 2 times, g is a kind of a monster, but we can do this, x plus 5 over 2 minus 5. Now let's simplify this. Well, that's 2 over 1. Those 2's will cancel, and I have x plus 5 minus 5. That simplifies, and then it's just x. Okay? So f of g of x is x. Now I do g of f of x. So take my g function, but instead of x, I'm going to replace it with all of f. So I do 2x minus 5 plus 5, all of that over 2. And let's simplify. 2x plus 5, or no. Two x minus 5 plus 5 over 2. Well, the 5's will zero out, and I have 2x over 2. The 2's cancel, and I have x. Well, look, they both came out to be x, so they are indeed functions. Okay? So you're doing compositions one of the other. Now I want you to try this one. I want you to determine, are these two inverses of one another, and be prepared to defend yourself. Okay? Multiple ways I showed you how to defend yourself, but I want you to try them. Okay?